Chapter 14, Quantum Mechanical Postulates, Section 14.3, Quantum Mechanical Postulate 3. Quantum Mechanical Postulate 3 states that in any measurement of the physical observable, denoted by uppercase O of a system, the only values that will ever be observed are the eigenvalues associated with the eigenfunction of the O operator. Again, this O with a caret on top denotes the quantum mechanical operator O. We have this equation O psi equals O psi. On the left, we have a operator O with a caret on top. On the right hand side, we have a constant lowercase o multiplied by psi. So if this equation holds true, then psi is an eigenfunction of the quantum mechanical operator O. The lowercase o is the corresponding eigenvalue. This lowercase o must be a constant to be the eigenvalue. When the function psi satisfies this equation, we say psi is an eigenfunction of the O operator. The condition is simply O psi over psi is a constant, and that constant is denoted by a lowercase o. So over here, if you apply the O operator to psi and then divide by psi, if the result is a constant, we say the function psi is an eigenfunction of the O operator with the corresponding eigenvalue, which is that constant denoted by lowercase o. Here's an example. Sine kx and cosine 5kx are both eigenfunctions of the second derivative operator, assuming k is constant. And now let's just evaluate this. Let's apply the operator to the function and then divide it by the function. Let's try sine kx. I'm applying the second derivative operator to sine kx. I got negative k squared sine kx, and then divided by sine kx, the result is negative k squared. Since k is assumed to be a constant, so indeed when we apply the operator to the function and then divide it by the function, we get a constant. That means sine kx is an eigenfunction of the second derivative operator. The corresponding eigenvalue is negative k squared. What about cosine 5kx? Again, we take the second derivative of cosine 5kx. The result is negative 25k squared cosine 5kx. Now divided by the original function, we get negative 25k squared, which is a constant. That means cosine 5kx is an eigenfunction of the second derivative operator, and it has a corresponding eigenvalue of negative 25k squared. If the wave function psi of a system is an eigenfunction of O operator with eigenvalue lowercase o, then any measurement of this quantity uppercase O of this system will yield a value of the lowercase o, the eigenvalue. For example, if the wave function of a system is e to the power of negative ikx, where k is a constant, I is the square root of negative 1, then it's an eigenfunction of the momentum operator. Let's try this. Let's apply the momentum operator to the function. We have negative ih bar d over dx, the e to the power of negative ikx. We take the first derivative, we get negative ik here, and then we have this exponential function. The result is negative kh bar multiplied by the wave function e to the power of negative ikx, and therefore this negative e to the power of negative ikx is indeed an eigenfunction of the momentum operator, and also the corresponding eigenvalue is negative kh bar. That means if we measure the momentum of such a system, the measured value is always negative kh bar, the eigenvalue here. This system has a exact momentum, negative kh bar in the x direction. A function may be an eigenfunction of one operator but not an eigenfunction of a different operator. For example, sine kx and cosine 5kx are both eigenfunctions of the second derivative operator, but they are not the eigenfunctions of the momentum operator. We can double check. We can apply the momentum operator to sine kx and divide by sine kx. Well, the result is definitely not a constant. Sine kx is not an eigenfunction of the momentum operator. Same here, if we apply the momentum operator to cosine 5kx and divide by cosine 5kx, we're not getting a constant here, and therefore cosine 5kx is not an eigenfunction of the momentum operator. Although a measurement of the physical property O of a system must always yield one of the eigenvalues, the initial state of the system does not always have to be an eigenstate of the operator O, which means, well, O psi over psi may not be a constant. So what will happen if you try to measure the physical property O? In this case, the measurement is probabilistic, like the outcome of buying a lottery ticket. When you buy a lottery ticket, what will the outcome be? We don't know. You might get nothing. You might get $1 billion. You might get some other amount in between. We do not know. It's all about probability. So if we have an arbitrary wave function psi, well, it can always be expressed as a linear combination of the eigenfunctions of any given quantum mechanical operator. So we have this equation. This psi is an arbitrary function. It can be expressed as the sum of ci psi I. Ci is a coefficient. Psi sub I is an eigenfunction of the O operator. So really, even if this psi by itself is not an eigenfunction of the O operator, it can be expressed as the sum of many eigenfunctions of this O operator, and very likely we have a infinite number of terms here. So this I is from 1 to infinity, and again C sub I is just the coefficient of psi sub I. C sub I squared has a physical meaning. That's the probability of having this system appearing in this eigenstate. Here's the example. If the eigenfunction of a system is sine kx, where k is a constant, we know that sine kx is not an eigenfunction of the momentum operator. We double check this. We apply the momentum operator to sine kx and then divide by sine kx. We did not get a constant. But however, we have this wave function expressed as a linear combination of the eigenfunctions of the momentum operator. And this is the momentum operator, and right now I'm expressing the sine kx as a linear combination of two eigenfunctions of the momentum operator. We can verify that e to the power of ikx is an eigenfunction of the px momentum operator with an eigenvalue of k times h bar. We can also verify this e to the power of negative ikx is also an eigenfunction of the momentum operator with an eigenvalue of negative kh bar. I'd like to verify these two are both eigenfunctions of the momentum operators with eigenvalues of kh bar and negative kh bar respectively. So again, if we have a function here, sine kx, that is not an eigenfunction of the momentum operator, well, it can be expressed as a linear combination of the eigenfunctions of the momentum operator. So we will get around the problem here. So if we try to measure the momentum of this system with a wave function of sine kx, well, sometimes we will get a measurement value of kh bar, sometimes negative kh bar. Again, we can verify that both e to the power of ikx and e to the power of negative ikx are the eigenfunctions of the momentum operator. Simply by applying the momentum operator to this function, we get kh bar multiplied by this function. We can apply the momentum operator to the other wave function e to the power of negative ikx, and we get negative kh bar times e to the power of negative ikx. We have another eigenvalue here, negative kh bar. So we know if we apply the momentum operator to this sine kx, and this sine kx by itself is not an eigenfunction, it's a combination of the eigenfunctions, then, well, what are we gonna see when we measure the momentum of the system? The result is probabilistic. The result can be kh bar or negative kh bar with 50-50 chance. Alright, so if you try to measure the momentum of this system, sine kx, well, it's possible you get kh bar, it's possible you get negative kh bar, each with 50% chance. And again, initially this system does not really have an exact momentum because it can be negative or positive kh bar. However, after the first measurement, the initial wave function of the system, sine kx, will collapse into one of these two eigenfunctions. Alright, either this or this, 50% chance for each. Alright, and also it's going to yield a result of kh bar or negative kh bar. So if you want to measure the momentum again, if the first measurement is kh bar, that means the system now has a wave function of e to the power of ikx. And then if you measure the momentum again, you get kh bar again. You measure it a third time, kh bar. You keep measuring the momentum of this system. Well, only the first measurement is probabilistic. It can be plus or minus kh bar. But the second, third, fourth, fifth, sixth measurements all agree with the first measurement, only because right after the first measurement, the wave function of the system is no longer sine kx. It collapses into either e to the power of ikx or e to the power of negative ikx. And then if you keep measuring the momentum of the system, you will get the same eigenvalue repeatedly. Now let's look at one example problem, 14.3.1. Let's say the wave function of a particle in the one-dimensional world is this. Psi is 0.6 times e to the power of ikx minus 0.8 times e to the power of negative ikx. This end, don't worry about this. This is just a normalization factor. I introduced this end just to ensure that the integral of the squared modulus of psi over the entire space is 1. Now let's measure the momentum of the system. Psi is a linear combination of the two eigenfunctions of the momentum operator e to the power of ikx and e to the power of negative ikx. Again, we can easily verify these two are the eigenfunctions of the momentum operator. They have eigenvalues of kh bar and negative kh bar. So if you try to measure the momentum of the system with a wave function of sine kx, well, the measured value is probabilistic. If you want to measure the momentum of this system, okay, this is not sine kx. Alright, this is not sine kx. It's just a different wave function. If you try to measure the momentum of this one, well, with 36% probability, you'll get kh bar. 64% probability, you'll get negative kh bar. Why 36%? Well, the probability is proportional to this coefficient squared, and this probability is proportional to this coefficient squared. So if we square both, we get 0.36, and this is 0.64, and now we have 36% versus 64% chances of getting kh bar associated with this eigenfunction, or negative kh bar associated with this eigenfunction. Again, this is just the first measurement. After the first measurement, the wave function of the system collapses into either e to the power of ikx or e to the power of negative ikx. And then the second, third, fourth, fifth measurements all agree with the first measurement. So if you try to measure the momentum of this wave function repeatedly with 36% chance, you'll get kh bar, kh bar, kh bar, kh bar, kh bar. With 64% chance, you'll get negative kh bar, negative kh bar repeatedly.